Hello everyone, welcome to lecture 6 on finite element method. In this lecture, we want to talk about truss structures and assembly of truss structures, but now we go to 2D. Okay, so these are essentially truss members or truss structures, but in 2D. Now, again, a truss member is similar to a spring, and then you can maybe think of this as spring combinations in 2D. And that truss member or spring itself is a one-dimensional element. So it's not still a two-dimensional finite element, it's a one-dimensional element in two-dimensional space. Okay, but we will possibly not finish the discussion today. We open it up, so we learn how to assemble them first, and then how to calculate the stiffness, and then we finish the example that we start today actually on next week. A little overview of what we have done first. So you remember again, we started from basically nothing. So we knew from our previous courses just a very simple spring, and the fact that the stiffness of that spring, if it is K, then the relation for that spring is F equals Ku. And then we learned that by just numbering these nodes and these nodes, and then the forces and displacements associated to those nodes, you can write the system of that spring like this. And then this system F equals Ku, it turns out to be a sort of canonical system or central system for every finite element method. And again, as I mentioned, if we learn how to handle this one and how to work with the spring combination, later we will save time, and it pays off when we do actually finite element. So that's the idea. And then we learned how to assemble this, and we said, well, basically assembling elements is like putting people together. Each person is like an element, it has a name, or in the case of element, it would be the number, and each person or element knows what is left or right, or what are the orientations. And then if they have some elements in common or some hands in common in here, then you can know that at that global node, then what information comes from what element. And then we looked into this example here, for instance, and we showed that for each of these elements, we can write the associated global numbers for each element. And then that information is basically very useful when you want to assemble it, and that's what happens. So you basically assemble a system like this, and you are done. The problem is still that when you do that, obviously you would have, I don't know, in this case you have 4 nodes, so you get a stiffness that is 4 by 4, get a displacement that is 4 by 1, and a force that is also 4 by 1. The issue is that on that system, on different nodes or on different points, you are applying different types of boundary conditions. So we mentioned that we have 2 types of boundary conditions in the finite element method to implement. One is the so-called Dirichlet type boundary condition or displacement type boundary condition. The other one is the Neumann type boundary condition. Now, the Dirichlet type boundary condition could be homogeneous or non-homogeneous. Neumann type boundary condition also could be homogeneous or non-homogeneous. And then we explained that now if you put those boundary conditions, you can see that the system is somehow complicated to solve, because there are things that you know and you don't know, but they are ordered in a way that it is fairly complicated to solve the system. So what we want is a system which is ordered like this. We want everything that is unknown, or the displacement, sorry, not everything, the displacement that are unknown to be on top here, and the forces that are unknown to be at the bottom there. So you need to sort of list your nodes, or you need to give them a degree such that all your degrees of freedom, so all the freedoms, they come up. The degrees of freedom are the points for which you don't know what the displacement is. So these are the unknown displacements. You want them on, and then the prescribed points, you want them at the bottom. And then we said, if we do that, or if you learn how to do that, then your system would look like this. And then you can do this very nice little thing that we usually call static condensation. And that brings you to your reduced system. And you can quickly solve that reduced system. And then we looked into an example we had previously. So we said, let's say, if you think of that example, for each of those nodes, which had their numbers 1, 2, 3, just from left to right, if based on their boundary conditions, we wanted to order them, this would be the proper degree. So this would be the way that we would love to degree them, or we would love to assign a degree to them. But the trick is then, or the next question was how to do it, let's say, systematically. We were looking for a systematic way to assign these degrees, and then that is what we discussed in the last lecture. I mentioned a little example here, and then that example basically tells us how to sort a few people that are left-handed or right-handed in a manner that all the left-handed ones are on the left and all the right-handed people are on the right. And that process, in essence, is very representative of what we do in the finite range method. And that's what we want to do today. So we kind of use that information, and then we ended up here. So we learned that there is this thing called extended node list. And that extended node list basically is like a node list. So this thing is node list. The first part of extended node list is just node list. So the first two columns. And then it looks like you are adding these informations to it to make it complete, okay? And then obviously in this, let's say in this table of information, what we haven't included yet, and you will later include in your, let's say in your code, would be two more columns. So let's say if I just take the same system, and let me clean up this algorithmic approach. So also at each point or at each node, you want to know if you have displacements or forces, okay? So, or let's say how much displacement or forces rather. So let me just put that information here. So displacement maybe here and force here. Okay, so basically this is the complete picture of your extended node list. So now you know on these two nodes have displacements, but the question is how much, right? So that would be the information that comes here. And then on those other nodes, you know, you have forces. So that would be the information that comes there. So basically what I'm trying to say is that, just find, yeah, is that, for instance, in this case at node 1, so this is node 1, this is the node that you have assigned degree 3 to it, the displacement is 0, right? So this would be a 0. At node 4, the displacement is, I don't know, it's a prescribed displacement that you have applied. Maybe it is 2, maybe it's 5, maybe it is 7 or -2, it doesn't matter. It's a number, it's prescribed. And then these two are unknown components. So eventually, when you solve the system, you will fill out those zones. And then also you have the forces. So on node 2 and 3, the forces are 0. And then obviously in these 2 points, you don't know the forces. Okay, so now if you look at this system, you have your node list, and then you have 6 columns. This is exactly how it works. So you always have your node list, and then again, if you program it in MATLAB, really, you don't necessarily need to sort or store the first column, because that would be your the index, the row counter in your vector, for instance. So that is anyway not a discussion, but you have 6 columns. And as I said, this is possibly only our way of doing it. This is kind of standard or anything. It's just a way of doing it, and I think it's a very good way. And also, maybe you have watched the YouTube videos for implementation. So those videos, they also sort of follow exactly the same. Some I don't know, maybe in those videos or in other lectures, I am not very careful about where I put displacement of force. So, but you should just know yourself. It's okay if you mix this up, but if you do it right, then it's no problem. Okay, so you have 6 columns. Now, if instead of this system, we had the same system, but now in 2D. So if we had a similar system in 2D, what would happen? That's what we want to discuss next. So let's say truss structures in 2D. Until now, we talked about 1D. And by the way, I mentioned this again. I think I mentioned it last time. Your node number doesn't matter. This is just completely arbitrary, obviously. What counts is the degree. Okay, so from now on, we mostly talk about degrees of nodes. And this degree, again, if you think about these ones, these are degrees of freedom, and these are more like degrees of constraint. But these are eventually the degree of the point. These are the identifiers of those points. Okay, so this is how you identify the behavior of your points or nodes. Okay, so let's think about a 2D problem. Now, if it's 2D, and then for a 2D, for instance, you can think of a simple system like this. Okay, so okay, it's not good we have 4 nodes. Let me just remove this so that, yeah, so that we also have 4 nodes here. So for instance, these are now your nodes 1, 2, 3, 4. If you think about it, each point has 2 coordinates. So this would be x of node 1 and y of node 1. This would have x of node 2 and y of node 2. The same here, x of node 3, y node 3, and x node 4, y node 4. So that means here in the coordinate, instead of one coordinate, we would have two coordinates. So you would have x and y for each of these nodes. Now, for each of those, also, you can have a different type of boundary conditions, different type of boundary condition. So you can think, for instance, of a node that is on a roller like this. Then it can move in the x direction, but in the y direction, it's basically fixed, right? So it's free in x direction. That means you can actually apply a force in x direction if you want to. So that's a Neumann type. In y direction, it's fixed. It's you are actually prescribing the displacement, and you are saying that displacement is 0. So that's a Dirichlet type boundary condition. Now, if that roller was rotated, obviously, then you get the opposite system. Okay, so now here y is Neumann, your x is Dirichlet. It almost never happens, but you can even think of complicated cases like this. You can even have a roller with an angle. So that basically tells you that you need to rotate your coordinate system. And if you rotate your coordinate system, then in this direction, it's free, or this is your Neumann direction. This is your Dirichlet direction, because it cannot move in that direction. So basically what I'm trying to say is that if you want to play this game again, now instead of one information here, you would have also two information there, okay, or two information pieces. So that means also the temporary degree, and then the degree and the displacement that you have on each of those coordinates and the forces, they also have two components. So everything that you have here, if this problem is 2D, it's going to have two information or two pieces of information. So it's going to have like x1, y1, and so on. And then, I don't know, let's say you would have the same game, whether it is Dirichlet or Neumann or something. And as I said, I mean, they can be different things. I'm not drawing this particularly for this system or anything. I'm just saying that you can have any of these. You can have Dirichlet in x direction. So this means Dirichlet in x direction, Neumann in y direction for node 1. This means for node 2, we have Neumann in x direction, Dirichlet in y direction. This means the node is completely fixed, so it is Dirichlet in both directions. In which case, this means you just have a usual, fixed support like this. And then if it is both Neumann, it means just it's a free point in the air. So it is not constrained in any of the two directions. All right, so you do that, and then, okay, you play the same game that we played with those numbers. So let's say if it is the thing, or if that system have this type of problem, then this would be like a -1, this would be a +1, and then this would be like a 2, this would be, I don't know, a -2, then this is a -3, -3 maybe, and then this would be like a, sorry, -3, -4, obviously. And then this would be like a I don't know, 3 and 4. And from that, you can kind of assign your global degrees. So for the system, this would be 5, 1, I don't know, 2, 6, 7, 8, 3, 4. So these would be the degrees that you would have on those nodes. And then, okay, you would have some sort of displacement and forces in the next 2 columns. But long story short is that, remember, this thing was 6 columns before. Now it is 6 times 2 columns, so it's 12 columns. Okay, so your extended node list for 2D is 12 columns. For 3D is going to be 18 columns. And then again, that is excluding the node list itself, which, as I said, in something like MATLAB is usually coming free of charge. So now, in order to kind of make this example maybe more meaningful, I'm going to clean up this orange system and then sort of draw a system that satisfies the conditions that we just drew. So let's think of just the same picture. Let's think of this. Now, if I ask you to draw constraints on this system such that it corresponds to the numbering that we have at the bottom, and then let's say this is node 1, this is node 2, node 3, and node 4. So at node 1, we said we want Dirichlet in X direction and Neumann in Y direction. That means the support that would do that is going to be something like this. Okay, now this makes sense. At node 2, we said the opposite. So if we have a system with sort of the degrees that we showed there, this should be the support condition at 2. At node 3, it's completely fixed. So I'm going to just draw one of these. You can draw like this. It doesn't matter. It just means it's completely fixed. You know the rollers and the, let's say, the fixed support illustration. Okay? So that's that. And then finally, if it is both Neumann, then, well, node 4 is both Neumann. So it is what it is. You don't have to add anything to it. It means it's free in both directions and you can apply forces in both directions. So it is what it is. And as you can see, that means you have now a system with 4 degrees of freedom. Okay, so this is kind of the game to play here. Do you have any question? Now, we talked about node list, and then let's say it's extension to extended node list, because we want to include all that information within the node list, which we call it again an extended node list, to solve the system. Extended node list, but the information, the information, the connection between the nodes, it's not there yet, and we call that actually connectivity. So we need to also store something else that we call connectivity. Now, connectivity is how it is usually called, but because we call the other one node list, and then again, in in our language, when you code this thing in the code, we call this NL, we call this ENL, and connectivity doesn't look good. We are going to call this EL. So we actually refer to it as element list, which makes perfect sense. This is the list of elements, essentially. Okay, so connectivity is essentially the same thing as element list, and I'm going to explain that by an example here. So let me just draw the system. Okay. So again, we work on a truss structure for simplicity here. So that's your structure. And then now you have the nodes. These are the red points. And as I mentioned, usually I number the nodes in with circles around them. So this is kind of our way of numbering nodes. So let's say this is node 1, maybe. This is node 2, node 3, node 4. And then we come down maybe, and we call this thing node 5, node 6, node 7, and node 8. Now, we can also include our support information. For instance, you can think this is a bridge or something. So you can imagine you have a, let's say, a fixed support here, or a usual structure that you would solve in mechanics of materials, and then maybe you have a roller here. So this is the support condition. Maybe also to make it more interesting, I put one here. Now we want to add the information about the elements. So let's say this is element 1, this is element 2, element 3, and now you can see, well, here you can also distinguish by colors, but the square around the number means it is element. So maybe we call this element 4, element 5, 6, and 7 is this diagonal here, and then 8 is the other one, 9 is the one at the bottom. I'm kind of trying to number them almost randomly so that you see there is no particular order here. We just number them the way we like. Okay, so this would be, let's say, your system. And now you can imagine, obviously, there are coordinates attached to this system. So we didn't talk about the coordinates of the points, but now in this other picture, I'm going to just write the dimensions. Okay, so imagine that these unit cells or these squares, they have dimension of 1. Okay, 1, doesn't matter what, just 1 unit of dimension. So basically, coordinate wise, you know that this point would be 0, 0, for instance. So x is 0, y is 0. And then, as I mentioned, you assume that these are squares, and then these distances, the vertical distance here is maybe just one unit. Again, it doesn't matter in which unit or in which dimension. Or in which system, basically. It could be 1 meter or 100 meter. So, and this is 1. So that means basically if you think about the width of the structure, that would be 3 altogether. Okay. So this is 3 and so, and this is maybe 3 and. All right. So now if you want to write the node list for this system, it's not something that you want to write, it's something that you must write. You have the node list number basically first. Okay, so let's put this here. And then you have what? 1, 2, 3, 4, 5, 6, 7, 8 nodes. So 1, 2, 3, 4, 5, 6, 7, 8 nodes. And in front of each node, you have their coordinates. So again, this is coordinate, which in this case, because it is 2D, it means X and Y. Okay, so we always have X first and then Y after that. And if you put the information you have here, for instance, node 1 is 0, 1. Node 2 is 1, 1. So if I just keep doing that, node 3 is, I don't know, 2, 1. Node 4 is 3, 1. Node 5, 0, 0. Node 6, 1, 0. Node 7, 2, 0. Node 8, 3, 0. Maybe you want to put a comma in between to distinguish, but as you know, for instance, if it is in MATLAB, you don't have to do it. So that's that. Now, you want to also write that element list or connectivity. Let me write it with a different color, maybe with green, so that it looks like elements. So we also have the element list. Now, how many elements we have? We have 14 elements. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I'm not going to finish it. So there would be a 12 and 13 and a 14 here. So what is the connectivity? What is the connectivity of element 1? The connectivity is, and then again, we just call it in a sloppy manner. We just call it element list because in our way, we really don't have the first column. It's just actually those numbers. So the connectivity is the order of the nodes in each element. So let's say for element 1, connectivity is 5, 1. Okay. So you can see this is element 1. Element 1 is between node 1 and node 5. And the order of the two nodes, the order doesn't matter. Okay, so you can write it 5, 1 or 1, 5. These are the global numbers. Everything is global at this level, okay? Again, inside each element, they know what is their local ordering and everything, but everything is global at this level. So that is 5, 1. Element 2 is between nodes 1 and 2. So maybe I write 1 and 2. Element 3 is between 2 and 3. Element 4 is between 5 and 2. Element 5 is between 5 and 6. Element 6 is between 6 and 2. Element 7 is between 2 and 7, and so on. Okay, so you would basically have your node list and element list. That's that way to go. And as I mentioned, for instance, if you have the system now, particularly for this system, we want to also write the extended node list. Okay, so element list itself is not complicated. Yeah, what we want to do is to kind of write the extended node list for this example. Okay, so let's remember the node list that you had here. So this was our node list, and you have the system. And what I want to write now is the extended node list for this. Okay, I put the system there to just see it. But we talked about the node list itself. It has 8 nodes. So let's say this is, I don't know, 1, 2, 3, 4, 5, 6, 7, 8. Obviously, we don't do it every time. This is the first time or the last time we do this, right? For an example like this. So this would be your node numbers. So this is your first column, and as I mentioned, depending on your language that you are writing your code, you may not have it really. This is your node number, and then you would have your coordinates. So for each node, you would have x, y coordinates. This is just the table we had previously, so it would be 0, 1. I don't write the comma in between to make it more like it should be. So this is 0, 1, 1, 0, 1, 1, 1, 2, 1, 3, 1, 0, 0, 1, 0, 2, 0, 3, 0. Okay. So again, the system looks to us like what it is. To the computer, it's just a bunch of numbers. That's the idea. We want to translate our way of seeing a system to the way that the computer likes to see the system. And then you have, again, the boundary condition information, but also you can see now for boundary condition information, you also have 2 columns to input. So this would be, for instance, node 1. You see it is free in x and y direction, so it is Neumann and Neumann. At node 2, it is Neumann and Neumann. At node 3, it's Neumann and Neumann. At node 4, it cannot move in the x direction, so it's Dirichlet, the displacement is fixed. And then Neumann in the y direction. And then at node 5, it is fixed in both directions. So it's directly here. Then you have again Neumann directly. Now what you want to do is to play that game of temporary degrees in the next two columns. So you would have X and Y, and now this would be your temporary degrees. And you just remember what we did. We said if it is Neumann, let's say you start from 0, and then if it is Neumann, you add 1 to it. And then if it is Dirichlet, you subtract -1 from degrees of constraint. So this would be 1, 2, 3, 4, 5, 6. And then you get a -1 here. 7, -2, -3, 8, 9, 10, 11, 12 -4, which by the way, you don't do this, right? So your computer does this numbering, this thing that we just did. This is something that your code is doing, right? So you just do basically this part. This is, you define your problem and then your computer does this numbering for you. This is not something that you need to worry about. And then as we spoke, then you basically take that and assign your global degrees based on that information. So again, that global degree obviously also has two components, so X and Y, or maybe you just call it degree or global degree, it doesn't matter. Degree. And now the plus numbers, they remain what they are. And the largest plus number, the largest positive number was 12. So now you add the absolute value of -12, so you get 13, 7, 14, 15, 8, 9, 10, 11, 12, 16. Okay, so this thing is exactly how you need to number your degrees, or the computer again does it automatically. You never see these numbers really, but this is exactly the way that it's going to be useful for you. And as I said, you would have two more columns, X, Y, and then possibly this would be, I don't know, displacements in that you apply on those, and these would be forces. Okay, so what I'm going to do next is I will just keep this for now, because the system really boils down to that. And based on that information, we want to know how the system would look like. So if you have that, let's say if you have this numbering, basically it means that you can write your system. Remember, we had 12 degrees of freedom, by the way, from the previous system. We can see it. 12 was the largest plus number here. Oh, sorry. Here. So if you remember that, it basically means that you can have a force vector here. So that's your force. Then this would be sort of your stiffness. And this would be your displacement. Okay, and in that system, you have 4 degrees of constraint. So let's say if you think about it like this, the stiffness matrix would look like this, and this is force. So this is your force vector, F. This is your stiffness matrix, K, which this is the global stiffness matrix after assembling it, right? So we have learned how to assemble them. So you put all these information, all the information from the elements according to their numberings, and then this would be your displacement vector, U. And again, if you look at these little parts, we call this thing, I think, U unknown. So these are the unknown parts of the U, and these are the prescribed parts of the U. And think of their sizes. This is like 12 rows, well, one column. This is 4 rows, one column. This is 12 by 12. Then you have 12 by 4. You have 4 by 12. And you have 4 by 4 here. So your stiffness would have this structure, basically, that you see here. And then here on top, the forces are known. So the forces are prescribed. Again, it's 12 by 1. But you know this. You don't know this, but you know those. You don't know this, but you know this. And then this is 4 by 1 again. So basically, at this point, or if you have done everything correctly until this point, and as I said, most of the things that should be done is done by your machine anyway, so it's not that you need a lot. All you have to do next is to pick basically this part of the stiffness, multiply it by this part, and then use that to solve for your answer using a reduced system of equations. So for this, you construct your, so you do that static condensation that we talked about. So it doesn't matter if it is 1D or 2D, really. The thing is exactly the same. That's a matrix operation. And then you come to your reduced system. And eventually your reduced system would look like, I don't know, AX equals B. And in that system, in that reduced system, A is this 12 by 12 matrix. Okay, so this thing is your this is your A. This is your reduced stiffness. This is that 12 by 12 matrix that we have up there. Okay, so this is kind of the summary of everything that I wanted to finish until exactly this hour, so until 9:20. So after this, we have learned how to handle, let's say, two-dimensional structure. Remember what we wanted to do? What we want to do is to learn how to assemble a system like this. So it's still made of truss members. So each member is like a spring, is a one-dimensional element, but we have it in a two-dimensional space. Now, we just learned together how to construct or how to generalize our extended node list understanding to two-dimensional problems. And we learned how to kind of write that and do the connectivity and come to the reduced system. The only thing we don't know yet is how to write the stiffness of an element in a two-dimensional problem or in a two-dimensional space. Again, if you just had a, let's say, a simple truss, let's say we said the stiffness or the effective stiffness is something like EA over L, which we said it could be something like K. Now, for that truss, if you had two nodes, the stiffness would have been K minus K minus K, K. That would be for node 1, node 2. Now, if that member is like that, the stiffness is going to be a 4x4 matrix, because at each node, now you have 2 degrees. The question is, what is the stiffness of that? And if we learn that, then we just write the stiffness of that member and assemble it exactly according to what we learned here and what we have here, and it's done. Really, it's not a complicated problem from that point on. So that's what we want to do after a break. I have 9:25 now, so let's have a 10-minute break. We continue exactly at 9:35. So see you in 10 minutes.
Sir, can I ask a question?
Yes, please.
Yeah, on the structure, I think I can see one more node in here. So element 7 and 8 intersects in a point. So can we say that this is also a node? Element 8 and 7.
Well, it depends. So actually, yeah, I mean, that's a drawing problem maybe. If what you said was correct, which could be, by the way, correct if you think of it as intersect. Think of these not intersecting if you want. But
Okay.
if you think of it as being intersecting, then you would also need a node here. And then, yeah, and so these wouldn't be just 2 elements, right? It would be 4 elements. So you need
Yes.
to add 2 more elements and 1 more node. But usually, if I want to do that, I draw this, a very clear point there, or that red point. Thank you for the question. That's a very valid question, by the way. I think it was my drawing problem. Yes, I mean, usually you should just maybe put a note here. Does that make sense?
Thank you.
Good. Thank you. Okay. See you at 9:35. Very good. So what we want to do next is to compute the stiffness of a truss element in 2D, to compute the stiffness of let's say I call it the stiffness of 1D element in 2D space. Now that 1D element, it could be a truss member or it could be a spring. Okay, so that's what we want to do. And I mean, if I want to draw the problem is really this. Let's say if you have a member like this, and then again, this is a 1D member, you can think of it interchangeably as a truss or as a spring. It doesn't matter. Let's say this thing has 2 nodes, and then we learned if, for instance, at node 1 you have F1 and U1, at node 2 you have F2 and U2, then the stiffness or the system of this element, it would be F1, F2, and then that would be K minus K minus K, K. That's what we started this lecture with. So this is perfectly fine. Now, I'm going to just take the same system or the same member. I duplicate it here. And now I will just turn it a little. So it's the same thing. I'm just turning it. This is the problem now. And you can imagine as soon as you turn it, the element stiffness itself, let's say it's a spring, is the same thing. It's the same element. It's just still K. But if you think of this as node 1 maybe, and this is a node 2 now. Now, each node has 2 degrees of freedom. So basically at node 1, which you previously had just F1 and U1, you would now have F1 in the X direction and U1 in the X direction. And then you have F1 in Y direction and U1 in Y direction. The same holds for node 2. You would have a similar problem. So for node 2 now you have F2 and U2 both in Y direction, and then F2 and U2 both in X direction. So for the rest of our discussion here, let's call this angle theta in this lecture. So this angle would be theta. So you can imagine basically if theta is 0, we should get something like this. But also that's not so easy because this thing is by nature a 2x2 system. Here you have a 4x4 system. Okay, so if we don't know anything else about this system, we know at least this. We know the stiffness of this system is going to be a 4x4 matrix. Okay, so these are the components. And then you can think of those, if it's a 4x4 matrix, that means each of these rows and columns, they correspond to a particular degree. So you can maybe think of it this way, that, I don't know, maybe this is for the degree 1x, this is for the degree 1y, maybe this is for the degree 2x, and this is for the degree 2y. Okay, something like that. So we don't know what this is. This is what we want to do. We don't know what this is, but we also expect it to be something of, or some function of theta. That is sort of a, educated guess basically here. So that's that. The other thing that we know about this is, let me just duplicate this slide. The other thing we know about it is that, as I mentioned, if you can write it like that, if you can write the system like that, you can imagine that if I also include the displacements and forces into this system, the system that we will be dealing with is going to look like this. So you would also have then your displacement sorted in a vector multiplied by that stiffness, and then on your left hand side maybe you get your forces also. So you have now your forces, and then you have 4 components for the forces, 4 components for the displacement. So you would have a system like this, and then maybe if you really want to put information here, you can do. Let me here it would be u1x, u1y, u2x, u2y, and then here you have f1x, f1y, f2x, f2y. So this is basically what you expect from this thing to do, and it looks like that. So we want to answer this question. This is this is the question we want to answer. So in order to answer that question, we start from one thing that we do know. If theta is 0, what do we expect for this system? So we start from that. If theta is 0, then the system would be a flat system. Right? So our system here, this would look just like that, except that now you have 16 components instead of 4 components. So basically it tells you that 12 of those components should be 0. And I'm sure you have a very good feeling or intuition which components should be 0, the components that are in y direction or have anything to do with y direction. So basically, all you need to do is to, if you want, is to assemble your system up here into this, or to sort it into this system. Okay, so you can see that now these 4 components, basically, they are sorted into the system, and then everything else would be 0. Okay, so this is what we know, or that's possibly the only thing we know. So we start from this. We know that if theta is 0, the system will look like that. All right, and I'm going to start the proof by doing exactly this. So let's say we do know that if theta is 0, we want to get that. Let's remove this. So I'm going to remove this and then make that original system a bit larger. So remember we had this system here. And the degrees of freedom that we just attached to it, a blue coordinate system. So now what I'm going to do is to attach a pink coordinate system to this, such that that pink coordinate system follows the direction of the element. So like that would be for node 2. So maybe I can make space here. This is node 2 here. So that would be now my F2 in the x prime direction. and u2 in the x prime direction. And this would be your f2 in the y prime direction and u2 in the y prime direction. Okay, so basically what I'm trying to say is that think of it this way, that you have a coordinate system, which is what we had previously. That is your xy coordinate system. That's the blue coordinate system. Now, I introduce a new coordinate system, x prime and y prime, with that angle theta that we had previously. Remember, this is the angle theta that we had up there. And now if I look at the pink coordinate system, this is very nice because it follows the, let's say, the truss or the element itself, and I can think of the coordinate x prime, y prime as that one-dimensional coordinate that we had previously. So all I have to do is to just put this here. And now I know if I had this system, which we don't know, the system at the bottom, we don't know. So I'm going to duplicate that. So we don't know what is this. This is x and y coordinate system, right? So you can see this is x and y. But what I'm going to do now is to assume that these are not x and y, these are x prime and y prime. So if these coordinates were x prime and y prime, in that coordinate system, the system would have, or the element would have looked like a 1D element. So it would have been k 0 minus k 0 0 0 0 0 minus k 0 k 0 0 0. Okay, so this is again, let's say x prime y prime coordinate system. And the question we want to answer is, what would be the answer for xy coordinate system? Okay, so this is really the only game we need to play. We need to just play the famous, I guess it's a famous game of rotating coordinate systems. Okay, I may or may not go into details depending on the amount of time we have left, because I want to finish it in one lecture. I tell you only, let's say, enough, and then I write the answer depending on how much time or how far we go. But you get the ideas. Basically, this is the idea. We know the system in the pink coordinate, or we know the stiffness in the pink coordinate, and now based on what we have here, the little coordinate system that I have here, I want to use coordinate transformation knowledge that you have, or we have, to transform the information that we know from the pink coordinate system to the blue coordinate system that we do not know. Now, the pink coordinate system, or the prime coordinate system, so I used pink color for the prime, so it starts with the letter P. So the pink coordinate system, or the prime coordinate system, it has its own basis vector. So every coordinate system is identified by its basis vector. So think about it that way, that we have ex prime and ey prime. These are the basis vectors in the prime coordinate system, or pink coordinate system, and then ex and ey. These are the basis vector in the xy coordinate system. Okay, these are the unit unit vectors that you usually know them. So if I want to kind of draw them, you would have something here which looks like, I don't know, EX. You would have something here. Let me use a better color, a dark blue. So this would be like a EX here. This would be like a EY for you. Okay, and then in the, let's say in the pin coordinate system, these two basis vectors would be like this. So that would be now your EX prime, and then this would be your EY prime. Now all you have to do is to write this, let's say the relations based on the angles between the two. You can quickly see that EX prime is cosine theta times EX plus sine theta times EY, and EY prime is minus sine theta EX plus cosine theta EY. Okay, so you have that. And using that information now, what you can do is to write your force vector from one coordinate to the other. Okay, so let's say if you have this thing, which you have the white one now. And now you have a force vector F in prime coordinate system. So in prime coordinate system, your force vector looks like Fx prime, Ex prime plus Fy prime, Ey prime. What you want to do is to change that, or to write it as Fx Ex plus Fy Ey. And that happens for each node, by the way. So it's just the coordinate transformation at this point. And then if you do the mathematical step, so if you just insert this information here, what you can see is this very nice system. So what you will see is this, that Fx, Fy can be related to Fx prime, Fy prime, using this sort of rotation matrix, if you want. Okay, so that would be the relationship which gives you Fx, Fy in terms of Fx prime, Fy prime. But also what we can do, and we will do, is that we can also do it backwards. So we can go, just put this information somewhere else, somewhere. Sorry. So we can put that information somewhere else so that I can write a little more. Let's say this is what it is here. So from this yellow system, you can also come to the inverse of that. So if you know what is the information, or what is the relationship taking you from a prime system, or x prime, y prime, to xy, then you can do also the opposite. You can also come from the xy system to the prime system. So I'm going to put the primes now here. And in doing that, all you have to do is to just have plus sign here, minus sign here. So let's just making it very clear about the sign, the signs of the signs of theta. So this is what happens. So this is the relationship between the two systems. Okay, and now again, to make it more clear for you, I make it like this. So the information that you see on about primes, I make them pink so that you can associate that with the coordinate system that we have. So these are the prime, the pink ones, and then these are the XY information are the blue information that you have in your original question. Okay, so this is basically what it is, and this is the connection or the key relationship to go from one system to the other. Once you have this, and when you are, once you understand this, the rest is actually pretty easy or straightforward at least. And that's what we are going to do. So let's say we know that we have this information here. We want to know what we can do with it. So if you know that, now I'm going to write, let's say, the entire force vector in terms of these angles. So I'm going to write something like this. And I want to write the pink one maybe on the left. So it's going to be like this: F1 x prime, F1 x prime, F1 y prime, F2 x prime, F2 y prime equals, you can now construct a matrix and I'm going to make that matrix yellow so that it reminds you of what you have just down there in yellow. So times the blue information, the information in the XY direction. Here, the forces. Okay, so you would have then F1x, F1y, F2x, F2y. Now, if you just look at these two systems, you can quickly connect these two. So all you have to do is to put this little box, one of them here and one of them up there, and then 0 elsewhere. And that's what I'm going to do now. So what you want to do is this: cosine theta, let's say sine theta, 0, 0, minus sine theta, cosine theta, 0, 0, and then you have here 0, 0, 0, 0, cosine theta, sine theta, minus sine theta, and cosine theta. Okay, so you have now the, let's say, the magic connection or the most important connection between the force vectors. And this is really the key to proceed with this problem. So as you can see, this is a big matrix, and I have to keep writing it, and I don't want to do that. So let's call this thing a rotation matrix, which is actually a rotation matrix, but let's just call it a rotation matrix R. Okay, so I'm going to do that, and now we want to do the same thing for displacements, and then we put displacements and forces together, and we are done. So basically, we don't need this little thing anymore. We just know the information we wanted. And clearly you can see this R is a function of theta. Okay, so basically the story here is that instead of all that big matrix, I want to write it as R theta. Or R simply. So this is the relationship between the forces from, let's say, the blue coordinate to pink coordinate system. Now, maybe you have a very good understanding or imagination about that, that if we do that for the forces, we should be able to write something like that for the displacements too, right? I mean, the forces and displacement in terms of these numberings and ordering, they are not very different. It's the same. It's the same story. It's a vector of displacement, vector of forces. So we just duplicate this thing, and now instead of all the forces, you can have, let's say, displacements. Again, obviously you can go through the steps and write it, but here we just kind of know that it's going to be the same thing. So you have, let's say, your system on the left, you have your system on the right. And then this R matrix, or this rotation matrix, it has this interesting property, if you pay attention to it, that it's inverse. So if you want to do exactly the opposite, so let's say if instead of going from blue to pink, if instead of going from blue to pink, you wanted to go from pink to blue, all you had to do is to use a minus theta for the R, okay? So I'm going to just put that theta at the here at subscript, so that we show that we are having the, let's say, theta. So the inverse of R, what I'm trying to say, that the inverse of R is just a rotation of minus theta, which makes perfect sense. So I mean, if you rotate something by 30 degree and then you rotate it by minus 30 degree, you come back to the same place, right? So you expect the inverse of that to be the same thing with angle minus theta. So this is the key here. So anyway, my point being that you could just write this thing if you wanted to. All right. So now let me just clean this up a little and then come back to where we started. So we know all these little things, and then this information here, I'm gonna keep it on the side for now. Remember where we started our question. The question was, if I know this, how can I go to this system? So the question was how to go from x prime, y prime coordinate system, or the pink coordinate system, to the blue coordinate system. And we have almost answered that. Okay, it's here. So you can clearly see exactly the same story here. Now you have all the pieces of the puzzle together. Basically, all you need to do is to put these pieces together. Okay, so now you know the system in prime coordinate system. you know how to transform these primes to the original coordinate system. Well, I mean, it would be the opposite of what is in front of you, but you know that. So basically, all you need to do is to just write that. So for the sake of presentation, I'm going to call this thing, let's call this K0, this thing, which is K0, right? I mean, let's call it, it's K0. It's like K if theta was 0. If you look at this system is something like that. It's like a f prime equals K0 times U prime. Okay, and then again, according to our, let's say, strategy, I'm going to use the same color. So now the next thing you want to do is to just use the information you have here. So instead of f prime, I am going to just write r theta f. So now I write it's the blue one. This is just this relation. That's equal K0. So it's exactly the system we have up there. And then instead of U prime, I write the same thing. So it's again R theta U. Now, if you multiply this thing by inverse of R from left, you get an identity here, and that is what we are going to do. So you get F equals R theta inverse, which you remember R theta inverse is the inverse, or is the R for minus theta, which is the same as the transpose of R. And then you have just U at the end, and then you have this K0. Okay, so now if you look at this, I can just clean that intermediate step. Now you see a similarity between the two systems. So your pink system is just F equals KU, or F prime equals KU prime. Your blue system is F equals something which has the flavor of stiffness times U. So this would be your blue stiffness. So basically you would say F equals, well, KU, and this R theta transpose K0 R theta, that is your blue stiffness. So this is your K. Okay. So long story short, I think this is kind of the proof of what we wanted to do. That from the pink system, you can come to the blue system. It's just that you need to be careful with the steps. And now at this point, we know that K is R theta transpose, let's say that K0 R theta. So what I'm going to do lastly is to just sort of spell out that system completely for you in terms of cosine and sine also. So we have all these little pieces. So we don't, at this point, we don't have to distinguish between the coordinate system or anything. We just answer the question we had from the beginning. Or maybe I claim too much. So the question we had from the beginning was this, right? So we answered that, and I'm going to just write that answer up here. Okay, so the answer is exactly what you have in front of you. So I'm going to just duplicate. Okay, so let's say if this is our force vector, then it would be equal. This would be the stiffness, and it's going to be a bit long. Maybe I take K out and then good. So in that coordinate system, that remember we had constantly this K thing. So K minus K minus KK. Imagine that K is out, and then we have 1 minus 1 minus 1, 1. Okay, so I'm going to take K out of the system. K is just the coefficient on the left-hand side of that. And then again, that if you have a truss, it's something like EA over L. If it's a spring, it's just the stiffness of the spring. And then here you want to have U1X, U1Y, U2X, U2Y. Then you have F1X, F1Y, F2X, F2Y. So if you play that little game that we just had, okay, so you know this is the stiffness, and then you know what is R theta. R theta is what we defined here. So this is what you need to do. I'm going to put this R theta on this little corner here for you too. So if you do everything correctly, and if I don't make a mistake, it's going to look like this. It's going to be cosine squared theta, cosine theta, sine theta. Then, okay, it's the same thing. Sine theta, cosine theta, sine squared theta. Okay, and then basically you will be dealing with a similar block. So I'm going to just copy that. Okay. So to have the same size, let me just also copy that thing again and put it up here. It's going to look like this, except a few signs here and there. So I put the signs with a maybe a slightly different color. So here you would have minus, 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 minus. And here you would have minus, 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 which maybe you have a good feeling why this thing is happening. So basically this is what it is. Okay, this would be your stiffness. And if you just look at it for a moment, and you insert theta equals 0. So let's just say now for an example, if theta is 0, if theta is 0 in this system, you can clearly see that you get 0 everywhere that there is a sinus, and then you get 1, -1, -1, and 1 for those 4 components. So this system naturally becomes what we expected or what we started with if theta is 0. So at least it seems we haven't made a mistake, at least for theta 0, okay? So if theta is 0, your system would be 1, 0, -1, 0, 0, 0, 0, 0, -1, 0, 1, 0, 0, 0, 0, 0. Okay, so this is the answer. This is the question we wanted to answer in the, let's say, in the second half of the lecture, and now we have it, and we just finished also. So it's 10:20, and I am glad that we arrived here. This is exactly what I wanted to cover, and then in the next lecture we will do an example with this, and with that we finish basically the first part of the lecture, that is understanding finite element with string combination. After that, we will go to, let's say, the mathematics of the finite element method. Do you have any question? Very good. Thank you very much for your attention.